Wait, do you just look at the deficit in the...
All right. Evening, everyone. We're having a quiz today. That's why it seems a little bit more packed in here than normal. I'm going to finish off the chapter on energy today. So, yesterday, or last session, we were talking about how energy is made, to transfer to one thing to other, and it's primarily just how something can do work. Right now, I got to kind of the final point I wanted to say about energy, which is that all energy in a system, if there is no non-conservative forces at play, all energy in the system will be conserved. So that's what we have up here at the top. We have the conservation of mechanical energy. We were talking about a couple different types. Last time we went over kinetic energy. I briefly went over potential energy. How just by changing an object's position, I can give it some energy. Say if I lift this box, currently it has so much potential energy. However, if I lift it up higher, I am increasing its height. Therefore, I'm giving it more potential energy. So you think of it as it has the potential to fall a greater distance and go faster and all this stuff. So that's this sort of process. That's gravitational potential energy. I also did a little example with some springs, more or less like a diagram picture, and show that there is something called an elastic potential energy. So if I compress or stretch a spring, so I'm adding energy into that system, the spring is going to want to return to its natural state. Similarly to like how all things on the ground just want to return to their lowest potential energy state. So we have potential energy, kinetic energy. If you go to another type of science class, there's chemical energy. There's going to be, I think in this class there's going to go over thermal energy. So when we talk about energy, it's just something, let me just do all of these. It's just a property that allows something to apply a force to another thing. And typically, or I should say, the big rule is that energy is never created or destroyed anywhere in the universe. So energy, as I push a cart or as you move your fridge or something in your kitchen, you're putting energy into the fridge. It is then, transferring that into, thermal energy as it rubs on the ground. Or let's say another example, we have, we've been going over like projectiles and things like that. So we have something that is moving quickly. Say that example of, I had the cannon, right? The cannon was moving sort of horizontally. It had a lot of kinetic energy, and then it was up off the ground. A lot of kinetic energy, a lot of potential energy. Eventually, it changed its position, so it changed its potential energy, and it kind of got a little faster as it got towards the ground. In general, let me go like this. So if there are no non-conservative forces acting on the system, the total energy within the system will remain the same. So this is like me saying energy initial is equal to energy final. And also, I could put on the same page, I could say something like, let's go like this. Nope, not that. This is just a capital E for energy total. And some, pages anywhere you might find it, it'll say like mechanical, mech, or something like that. It's up to you. The total mechanical energy of a system will be just adding all of those little bits together. So it will be adding the kinetic energy plus the potential energy. And this can be any of those types. It could be, gravitational potential energy, or it can be elastic potential energy. So I could keep it very general right here. So how can I sort of express this with maybe some physical demonstrations? I'm going to go over a few pictures so you can have them for later. Say, for example, I forgot to make that pop up later. So say I have a box somewhere floating up in space. I'm holding it. It has potential energy. It's not moving though. Sort of me holding it still. It has potential energy. Let's do this. So potential energy, no kinetic energy. It's not moving. So up here, let's look at the energy of the system. So again, energy total is kinetic plus potential. Up here, it only has potential energy. So the energy total up here, come on, is just potential because it's not moving. It has no kinetic energy. All right. Then I can convert all of that energy into the other form just by dropping whatever this object is. And we said gravity is a conservative force. So going back from that previous line, since it's just a conservative force happening, that means all of the energy in the system remains the same. If I drop it, it will speed up, and then think of it as the split second before it hits the ground. It will have as much speed as it can possibly have for me dropping it right here. So just that tiniest fraction right before it hits the ground, it's going to be moving its fastest. So at the bottom, down here, at the ground, right as it hits the ground, okay, now its height has changed. So let's look at the energy again of the system. Is kinetic plus potential energy. So in this case, its height has shrunk all the way down to 0. So let's do this. I'll just so I can have them up. Kinetic energy, that was 1/2 mv squared. And potential energy was mg, let's just call it h for right now. So the height off of the ground. So now that the height is practically 0, it has 0 potential energy. So we have something that has the total energy just equal to its kinetic energy. That's because potential energy, let's see, equals 0. That's like that. Okay, it could be the same exact thing. You might be able to see how you can use these equations instead of a lot of those complicated kinematic equations. You can now use these if your system is really perfect. So if we have this perfect ramp right here that is frictionless, so it will have no non-conservative forces. That means that it's sort of like sliding down this, block of ice. So we have the same exact thing. I could put a block up here. I could find its total energy at this tallest point. And let's say kinetic energy plus potential energy. Then we could say, the problems usually start out with this thing is at rest at the top. So since it's at rest, the velocity is 0. Same sort of case. And just like that. So if you are going in your notes, what you can do to make it just a bit more clear, I can maybe do it right now also, is that on all of the variables up at the top, I'm going to put as I for initial. This is the energy up here. So up here, and down here I'm going to put F for final. Okay. So we have sort of this secondary way of finding velocities, finding distances, things like that, just by using the energy of the system. We don't have to actually get a ruler or whatever we were doing last time, and mapping and drawing and measuring, or using those somewhat complicated kinematic equations. We can use these energy equations instead. All right. This one, this is an example of like springs. Same sort of thing. So let's say I have a spring that is compressed. And this is like the case in a lot of Nerf guns, a lot of toy guns, things like that. I don't have the spring ball out here, but we're going to compress a spring, so we're adding elastic potential energy to this spring right here. And I'll write elastic. And in this case, this is like where we have it sort of, ready to go. It sort of compresses the spring. There's a mass or a dart or whatever in front of this. Some sort of mass. And then you let it go. Somehow use a mechanism of some sort that lets the spring go. It lets it decompress. It goes back to its original state. And so, at this case, the mass or dart isn't moving. And in this case, Now, afterwards, the spring sort of transfers its elastic potential energy into the block as it flies out or does whatever. So in this case, now the elastic energy is 0 because it's transferred it all into that block, sort of moving along very quickly that way, which is kinetic energy. And so a lot of problems can come from, this block comes moving in and then it compresses a spring by a certain amount. How fast was it moving? Or what kind of properties do the spring have? Things like that. And it's just by transferring energy from one object to the other. So, a lot of neat things that we can do. Let me do one more sort of drawing example. We have this pendulum. We have a ball on pendulum. And let's say at the end, those are the highest points. So we have potential energy is, we'll say max up here. And if you know anything about pendulum, once it gets to that point, the other point, it stops moving. So kinetic energy at the end points are 0. 0. Same thing over here. But then, as the ball or whatever swings down in the middle, that will be considered the lowest or the ground state for the potential energy. So down here, we have kinetic energy is at a maximum, whereas potential energy is at a minimum or 0. Maximum equals 0. Okay. So I'm going to, let's see, 5, 10. Yeah, I need to get something set up. So I'm going to take about 5 minutes. You guys can talk to yourselves, whatever you want. I'm going to be setting up a sort of demo of this.
We did we watched a video of the bowling ball. If you have to fix a wall, you can't push it. Because if you give it a time, it'll hit you in the face. If you just drop it, so it's equal less than that. So it like looks cool. So people like that. Every time. That's not even. Oh. No. You can do that. They're really heavy. Cut out for that. So it's like it's summer furniture. It's been a while, but yeah, I got it. So like that's why I was still like the graphs before, because I was in calculus, so like it was just the derivatives. So.
All right. So, sort of prove that there's this conservation of energy. This basic sort of thing up here. This is the perfect example with no friction, anything. We have the ball on one side going exactly as far up on the other side. That's because energy will transfer from one form into another. So it'll go from potential energy all the way into kinetic energy, and then it will transfer back into potential energy again. The total amount will remain the same. So, sort of prove that, I have this bowling ball pendulum thing. And this is not a perfect example. This is, a messy example. We have a bowling ball, and it's connected with this very heavy rope. The examples in this and on all of your problems are with like a string or rope that is massless, which is physically impossible. So this is a messy example. So the energy throughout will kind of get a little less as time goes on. That's sort of why something like a tennis ball, basketball, anything that bounces, it will slowly start to get, bounce lower and lower. It's because it's not a perfect example. Energy is fading away somewhere, but it's not disappearing. So, in the case of a tennis ball, it turns into sound energy. It travels through the air. Then it also probably makes the ground a little warm as it hits the surface. And so, something like this, if it was exactly perfect, it would bounce up exactly to the same height of my hand. But this is a very imperfect ball. Same as this sort of example here. So if I give this some potential energy, and I have it right in front of my face, what you don't want to do is add some more energy, more than you need. So say if I what if I give it just the tiniest push? Oop. Maybe a little bit more. It's a lot heavier than I thought. Okay. A little, maybe a decent push. So you don't want to add energy to the system in this example. So if I do the problem, I will be perfectly fine. Okay, ready? That's because physics will continue to work no matter what. You deal with load. And there we go. All right. Now, I will ask if anyone wants to try this out. For volunteers. If you want, sit on down. Yes, awesome. Okay. Everyone, form a line. No. All right, same exact example. So I'm going to go all the way up and see where it hits chest. So let's, if you can, slide down and just sort of lean against the wall. And kind of up to your chin. Now just stand in a way that's comfortable. So you won't move. Okay. Maybe slide down.
Sorry to interrupt. Does anybody see a pair of keys in here? Sorry about that. We should be on not that stuff.
Does anyone see some keys or something?
It's okay. Sorry about that.
Okay. Good?
Yeah.
Okay. So thing is arms just out to the side.
Okay.
Okay. And don't move however you have it. Okay. Okay. There. There. All right. Awesome. Cool. Yeah. Anyone else want to try? So I'm going to have this up right now. Yeah, awesome. We got a bunch of people. What's that? With the grabber. If you don't want to do it in front of everyone, I'll have this up. You can do it at the end as well. Awesome. Here we go. Since we don't follow the knees, so we're going to do that. Okay. Bring it up. If you can, lean down a bit. Yeah, I got it. Like that. Makes it easier so you don't have to lean so far. There we go. Okay, just back against the wall. You can just have it kind of okay, and just arms out to the side whenever you're ready. Okay, perfectly still, perfectly still. Awesome. Good job. Anyone else? All right. Yeah, one more. Do one more, and then I'll leave it up. Anyone wants to try it at the end of class? It's just the simplest example of a pendulum, but it's, I was scared when I did it.
This is scary.
It is scary. So, previous person is good. Call my list. A little shorter. Okay.
Say it for me.
Pull it. Right in front of your face. Good effect. Okay. Now arms Out to the side here. All right, good job. All right, let's give like a round of applause. Okay, so we have. We have sort of this conversion of energy that used to be a lab that we do online. So like last year, we'd have you guys do a lab like this. It's pretty much showing what this whole pendulum thing was about. The total energy is the same, no matter where the person is on this ramp. But it's just being converted into a different type of energy. And somewhere in the middle, where it's not so high up, it has a combination of potential energy and kinetic energy. That's when they're both kind of like in the middle. It's at the end points or the extremes. It's where we have a lot of potential energy, at the very top there, and at the very top there. And then at the very bottom, that's when the thing's moving the fastest. All right. And finally, last sort of separate thing that's just going to be one slide is power. I really don't want to stab. Stab myself. Okay. Power is different than energy. Power is how much energy you use in a specific amount of time. So we have the equation of power is work over however much time has passed. So this is W for work, not weight or what you may see somewhere else. Work, time, this is power. The units for this, typically, we get into only talking about power when we're maybe talking about engines or things using electricity. So the units for power are 1 watt is equal to 1 joule over 1 second. So you can look at your light bulbs that you buy from Lowe's. Figure out that light bulb is using a joule of energy, or 30 joules of energy, it's a 30-watt light bulb, per second. So I don't know if I have too many power questions or examples right now. Anyway, that's pretty much the end of the chapter. You guys can put everything away. If you need a calculator, I have a handful of them up here. All right.